Namaste. Welcome to Murali's World of Physics. Experimental investigations in nuclear physics mainly comprise of the study of radiations or particles emitted from excited nuclei. Some nuclei are inherently unstable even in their lowest possible energy level, that is the ground state, and they spontaneously emit particles or radiation. These comprise of positively charged alpha particles, which are helium nuclei, or negatively charged electrons, or electromagnetic radiations in the form of gamma rays. This is the so-called phenomenon of natural radioactivity, which was discovered by Henry Becquerel in the year 1896. On the other hand, nuclei which are stable in their ground states can be excited by some appropriate means to one of their excited states, and then by their very nature of being unstable, they will subsequently decay to either the ground state or one of the lower levels with characteristic lifetimes, and thereby either radiations or particles can be emitted. If the excitation energy is above 8 MeV, it is often a particle which will be emitted, and if the excitation energy is below 8 MeV, it's usually a gamma ray which will be emitted. Excitation of the stable nuclei can be called artificial or induced radioactivity. This process was discovered by Irene and Joliot Curie in the year 1933. The basic principle behind studying the radiations or particles emitted from excited nuclei in order to get information about the nucleus itself is the fact that it is these radiations or particles which carry some sort of information about the nucleus from which they are emitted. However, these particles or radiations are extremely small in size, and they cannot be seen by the naked human eyes or even with the help of powerful optical microscope. So therefore, we need some sort of special devices in order to detect these radiations or particles, and such devices are called nuclear radiation detectors. Such nuclear radiation detectors form an integral and indispensable set of tools for any nuclear physics experiment. In general, such detectors have to satisfy the following requirements. First of all, the material of the detector should be such that the incident particle or radiation will interact with the material and lead either directly or indirectly to the production of charged ion pairs, so that in an applied electric field, these charges can be collected by the respective electrodes, and we can get an electrical signal at the output of the detector. So therefore, it means that for each incident particle or radiation which has interacted with the material of the detector should result in the generation of an electrical signal at the output. Then there is an optional requirement that the amplitude of the signal should be proportional to the energy deposited by the incident particle within the detector medium. Also, very often the exact time of arrival of the incident particle at the site of the nucleus with which the interaction takes place is also required for some applications. So therefore, the output electrical signal should have some time information relative to the time of incidence of the bombarding particle. Another important information is the angle at which these outgoing particles or radiations are emitted with respect to the direction of the incident particle. In fact, we derive what is known as the angular distribution or angular correlation from this information. Another optional requirement of a detector is that the output signal should contain information about the actual position where the outgoing particle was incident on the detector surface. Well, this is actually coupled to the angular distribution information. Of course, some of the requirements are optional. All the detectors need not satisfy all the above requirements. I would say the basic. Now, let us see the basis of the working of a nuclear radiation detector. Such a detector essentially comprises of an active medium. An active medium is a suitable material in which the incident particle enters and then interacts and finally produces an output electrical signal. Now let us see in detail the working of a nuclear radiation detector. So this is our incident particle which enters into the active medium, and of course, as I mentioned earlier, there will be interactions between the incident particle and the active medium. As a result of this, the particle will lose continuously energy as it goes deeper and deeper into the active medium. And if the total thickness of the active medium is more than what is known as the range of the incident particle inside the medium, then it will eventually stop. So here this is the range of the particle in the medium, and the active medium thickness is much more than this. So therefore, when the particle covers a distance equal to the range of the particle inside the active medium, it will lose all of its energy and then eventually it will stop. On the other hand, if the thickness of the detector medium is less than the range of the particle, then it will move further, lose energy, and then eventually come out of the medium with less energy. Now we see how the interaction proceeds and what is the result of that. So we can see that in interaction will result in the production of ion pairs, positive ion and negatively charged electrons. So this arises from the neutral atom which is ionized by the incident particle, and as the ionization proceeds, the particle loses energy, and of course this will continue and finally it will come out. Now if you have only this much arrangement, then the ion pairs which are produced by the interaction of the incident particle with the active medium, they have a strong tendency to recombine, and so therefore they will combine back into the neutral atom. Now, in order to be of any fruitful purpose, so we have to get an output pulse due to the interaction of the incident particles with the active medium. So therefore what we do, so we enclose the active medium by two parallel plate electrodes, anode and cathode, and then apply suitable potential difference across these two electrodes. So now let us see what happens when the incident ion comes and interacts and produces the ion pairs. Because of the electric field existing between these two, we have a collection of the respective ions at the anode and cathode. So the electrons are attracted towards the anode and the positive ions are attracted towards the cathode. Of course, we connect at the output electrical circuit consisting of a resistor and a capacitor and derive our output pulse from the other end of the capacitor. So we take the output here. So let us look at the variation of the voltage on the anode due to the collection of the electrons at the anode. So you can see that as the ion pairs are produced by the incident particle interacting with the medium and these electrons being collected at the anode, you can see that the voltage increases and finally of course the particle will go out of the medium. We know that electrons are much lighter than the positive ions. So therefore in the same electric field they acquire much larger velocities at a faster rate. So therefore they are collected by the anode very fast, of the order of nanoseconds. On the other hand, the positive ions, which are much heavier, will acquire smaller velocities correspondingly. So therefore they take more time to get collected at the cathode in time scales of the order of microseconds. So therefore the output pulse will have two distinct parts. The faster initial portion will be due to the collection of electrons at the anode, and the comparatively slower rising portion which takes place later will be due to the collection of the positive ions on the cathode. So if the detector is open-ended, then this pulse amplitude will saturate and stay without having a path to discharge. So the pulse shape will be like this. Now if we connect an RC network, as we have explained earlier, with a particular time constant, then the pulse shape will be something like this. Now let us see what are the different types of interactions of radiations with matter. It will essentially depend on the type of the particle or radiation which is incident on the detector. So we can have charged particles, we can have photons, or we can have neutrons. So firstly we consider the charged particles, for which there are two basic types of interaction, namely ionization and Bremsstrahlung process. So the charged particles interact with matter basically by the electromagnetic interaction, that is through the Coulomb force. Now this Coulomb interaction can take place either in the Coulomb field of the nucleus or in the Coulomb field of the atomic electrons. Either of these can take place. Ionization is the predominant process by which the charged particles interact with matter. So they essentially collide with atomic electrons, and in that process a part of the energy of the incident charged particle is transferred to the electron, and the electrons get ejected from the atom, obviously because they have enough energy sufficient to overcome the binding to the nucleus. So therefore there results an ion pair consisting of the ionized atom and the negatively charged electron. The maximum energy which can be transferred to the electron from the incident ion is given by kinematics, and this is equal to 4 me m0 e by me plus m0 the whole square, where m0 denotes the mass of the atom, me is the electron mass, and e is the incident particle energy. As the particle moves deeper into the medium, a series of such collisions take place, and at each collision the particle will lose a part of its energy to bring about the ionization process. So therefore it will lose its energy continuously. If the thickness of the material is sufficient, the ion loses all its energy and stops. So this particular thickness is called the range of the incident ions within the detector medium. On the other hand, if the energy is sufficiently larger and the range of the particle is larger than the thickness of the detector medium, then the ion will come out with less energy. The second type of interaction is the Bremsstrahlung. This is basically production of continuous radiation. We know from electromagnetic theory and that any accelerated charged particle will undergo radiation process, and this process will be dominant at high energies. Now coming to the photon interaction with matter, there are basically three types of processes which are important for energy loss of the incident radiation in the detector medium. These are the photoelectric effect, Compton scattering, and pair protection. Of course, I am omitting the elastic scattering process, which by the name itself we can understand that it is an energy lossless scattering. There is no energy loss. So therefore this elastic scattering process will not be important for producing charge ion pairs within the detector volume. So we don't consider elastic scattering at all in our discussion. The first process, namely the photoelectric effect, obviously this was discovered by Albert Einstein. So this essentially involves the interaction of the incident photon with one of the atomic electrons. So the interaction results in an energy transfer to the electron, whereby the electron overcomes the binding to the nucleus and gets ejected from the atom. So the energy acquired by the electron will be E is equal to h nu minus Eb, where h nu is the incident photon energy and Eb is the binding energy of this electron to the nucleus. So this will range from about 1 to 50 keV or so. This type of interaction is dominant for photon energies below 1 MeV. The second process is the Compton scattering, which is simply the scattering of the incident photon by one of the atomic electrons. In this process, again energy transfer takes place, and the electron will be ejected from the atom at a particular angle phi, and in the same time the incident photon will be scattered through some angle theta with a reduced energy. Why reduced energy? Because some energy has been transferred to the electron. So therefore E gamma prime will be equal to E gamma minus E. Now from the kinematics of this process one can work out the energy of the scattered photon as E gamma by 1 plus epsilon into 1 minus cos theta, where epsilon is nothing but the ratio of the incident gamma energy to the rest mass energy of the electron. The probability for this process will be dominant for energies near 1 MeV. Lastly, we have the pair production process, which is the creation of an electron-positron pair in the presence of a nucleus. So here, obviously, because we have to create the masses of the electron and positron, there is a threshold energy which is equal to 2 MEC square is equal to 1.02 MeV. So this process can take place only if the incident gamma photon has an energy in excess of this threshold value. So therefore, this will be dominant only for photon energies which are typically above 5 MeV or so. Now coming to neutron interactions. We know that neutrons are neutral particles, and therefore as such they do not produce any direct ionization, and therefore they cannot be detected directly, because the basis of detection process is the production of charged particles by some method. Therefore we will have to depend on some neutron interaction which will generate ion pairs indirectly. I will just point out some of these interactions. The first one is the N-alpha reaction on boron 10, producing lithium 7 and of course gamma rays. We have a neutron coming and hitting a boron 10 nucleus, and this will form a compound nucleus of 11 boron, which will disintegrate into an alpha and a lithium 7, and thereby an accompanying gamma ray also will be emitted. So the charged reaction products, namely the alpha particles and the lithium nuclei and of course the gamma rays, can produce secondary ionization in the detector medium, which will produce a detectable output signal. A second type of reaction is the fission reaction induced by neutrons. For example, the neutron induced fission on uranium 235, which leads to the fission fragments plus a few neutrons. So we have the neutron bombarding a uranium 235 nucleus and splits the nucleus into the fission fragments and a few neutrons. The charged reaction products, namely the fission fragments, are highly ionizing and can produce secondary ionization in the detector medium, which will produce a detectable output signal. So from either of these two types of reactions, one can generate secondary charged particles, which will in their turn produce the output signal of the detector. Now, whatever be the type of incident particle or radiation, and whatever be the type of the interaction, the incident particle will lose a fraction or all of its energy within the active volume of the detector. This leads to the creation of N ion pairs. N is equal to E by W, where E is the incident energy and W is a quantity which is called the average energy needed to produce one ion pair. So on the average, the incident particle will lose an energy W by creating an ion pair. So therefore, N is equal to E by W. Now the typical values of W for typical detector materials are given here. It's about 30 eV for argon, about 300 eV for sodium iodide, and about 3 eV for germanium or silicon, the semiconductors. The total charge collected at the electrode will be given by Q is equal to N times E, that is E into E by W. So therefore, the output voltage developed will be V is equal to E into E by W C, where C is the capacitance of the detector. Thus, the amplitude of the output pulse will be equal to K times E, where K is equal to E by WC. So these are constants, and therefore the pulse amplitude will be proportional to the incident energy. Therefore, we see that each incident radiation or particle which actually undergoes an interaction gives an output pulse, and the amplitude will give us the energy. The actual active medium can be either a solid, liquid or gas, and correspondingly we have a solid detector, a liquid detector or a gas detector. Historically, the gas detectors were the first ones to be used, chiefly because of the simplicity and the easiness of fabrication. The detector output pulses are usually in the level of microvolts or at most the level of millivolts. Now, in many cases, we would like to apply subsequent processing on the detector output pulses, and finally these will have to be counted. So therefore, for easiness of these procedures, we have to amplify these pulses at least to the level of a few volts. So definitely we need an amplifier. And also the shape of the output pulse from the detector is not quite suitable for the subsequent processing and counting. So therefore we have to do some sort of wave shaping on these pulses. So therefore when we pass these pulses through the amplifier, we get an amplified pulse and also a reasonably well shaped pulse. So that is the function of the amplifier. We would like to know how many output pulses are there with different amplitudes, or essentially what is called the pulse height distribution. In other words, if we keep in mind the proportionality between amplitude and energy, this particular pulse height distribution will give us the energy distribution of the incident radiations also. So that is the purpose. We want to know the energy distribution of the incident radiations. Now this is a typical pulse height spectrum of gamma radiations incident on a gamma detector. You can notice that there are actually three structures in the spectrum. The main important structure being the photopeak. Now this is basically arises from the photoelectric effect, and below that we have the portion which arises from the Compton scattering process. Now this is a generalized detection system for any radiation detector. So we have the detector which is powered by a suitably constructed high voltage supply. Then these pulses are amplified basically in two steps. The first one is known as a preamplifier, which will be a stage which is very close to the detector, and then maybe at a longer distance we can have a main amplifier. And these pulses, for testing purpose, we can observe them on an oscilloscope. In order to get the pulse height spectrum, we have to sort these amplified pulses according to their amplitudes. So this will need a discriminator, and then finally we have to count the pulses. So we can have a basic system comprising of these modules, or we can pass the output amplified signals to what is known as a multi-channel analyzer, which will give the pulse height spectrum in one go. Or alternatively, we can pass the amplified pulses to a personal computer, where a suitable software can do a lot of things with the output pulses. So now, as I mentioned earlier, the photoelectric peak is due to the photoelectric process. So here there is a complete absorption of energy of the incident radiation. On the other hand, the Compton distribution, there is no complete energy absorption. That is why the Compton distribution occurs below the photoelectric peak or photopeak. Here, part of the energy of the incident gamma radiation is transferred to the electron, and the remaining part will get ejected from the detector because of the scattered gamma ray escaping from the detector. And this distribution will depend on the angle at which the Compton scattering takes place. So therefore, this has a maximum corresponding to 180 degree scattering, and that is where the Compton edge occurs. So the plot of counts versus amplitude is what is known as pulse height spectrum, and the main feature is a characteristic Gaussian peak which gives the energy of the incident radiation. So therefore, the plot of counts versus amplitude, which is known as the pulse height spectrum, and the main feature is the characteristic Gaussian peak. The width of the Gaussian peak will give us what is known as the resolution, and the amplitude of the photopeak will give us the energy information. So I am just concentrating on the photopeak. So there is a particular width which I have indicated by gamma. So this gamma essentially gives us the resolution. That means to what extent the detector is able to distinguish between neighboring energies of the incident radiation. So that gives us the resolution, and the amplitude will give us the energy. For example, in this particular case, the energy is about 5.46 MeV. Now, detector resolution is expressed as the ratio of the full width and the amplitude of the photopeak, usually as a percentage. So R, the resolution, is equal to 100 into gamma, the full width, divided by the peak amplitude. The resolution usually depends on the detector type and the gamma energy. For example, for 1 MeV gamma rays, the typical values range from around 1% to 2% for high resolution detectors like CLE and HPGE, to about 7% to 12% for poor resolution detectors like sodium iodide. Another important characteristic of a nuclear radiation detector is what is known as its efficiency. From our earlier discussion, it should be evident that all incident radiations or particles need not interact within the detector volume and give rise to a pulse. So the actual number of detector output pulses need not give us the total number of incident radiations. So the how good or how efficient the detector is decided by what is its efficiency. This is represented by eta, and this is nothing but the fraction of number of incident particles or radiations which actually get detected. So this will depend on the interaction cross section and dimensions of the detector, and of course on the energy of the incident radiation. Charge particle detectors essentially have an efficiency equal to 100%, so eta is equal to 1, whereas photon detectors have efficiencies which are less compared to 1. The type of a detector depends on the type of the particle or radiation that is to be detected. For charged particles, we have silicon surface barrier detector, which has higher resolution and complete efficiency, 100% efficiency. For X-rays, we have what is known as the lithium drifted silicon detector, SELI, where the efficiency is 1 for low energies and has very high resolution. On the other hand, for gamma rays, which have energies much higher than X-rays, we use either the scintillation detector or the HPGE detector. The scintillation detector has efficiency less than 1, obviously, and the HP detector also has efficiency less than 1, but between these two, the choice will depend on the resolution. The scintillation detector has a poor resolution as compared to the HPGE detector. So if you want good resolution but we can forego efficiency, then we will go for the HPGE detector. On the other hand, if you want better efficiency, then we will go in for the scintillation detector. Now there is a necessary procedure which is to be followed before using any nuclear radiation detector for any particular experiment, that is the energy calibration. To get the energy of the incident particle or radiation from the output pulse amplitude, we have to know the following relation, which we have already seen. There is a linear relationship between the pulse amplitude and the incident radiation energy. V is equal to K into E, where K is a constant, and this will have to be known if you want to determine the energy of a radiation from the observed pulsate. So experimentally this is achieved by observing the pulsate of various incident radiations of known energies, and for this purpose we have standard reference radioactive sources where the energies of the radiations will be known accurately. So this procedure is called the energy calibration of the detector. This is what results from such a procedure. So we have a plot of the gamma energy versus the observed pulsate. We make use of standard reference sources which emit radiations of known energies. So we have a cobalt 57 source, barium 133 source, cesium 137, cobalt 60, and so on. There are other sources also. So here the energies of the radiations are quite accurately known, and if we measure the output pulsate corresponding to each of these radiations, then we can plot this linear curve, and from the slope of this that's what we do by the energy calibration. We get the value of the slope. So once K is known, then for any unknown radioactive source, just by observing the pulsate, one can determine the corresponding energy of the radiations. I will just mention some different types of nuclear radiation detectors. We have gas detectors, for example, ionization chamber, proportional counter, Geiger-Müller counter. We also have scintillation detectors. One example is the sodium iodide detector. Then we have semiconductor detectors, of which the silicon surface barrier detector is a good example and is used for charged particles. Then we have what are known as lithium drifted detectors, SELI and JLI. So these make use of the semiconductors, silicon or germanium. Also we have high purity germanium detector. Now I will be discussing the details of all these types of detectors in my upcoming videos. I will end this video at this point. I'll be back soon with yet another video on basic principles in physics. Till then, goodbye.